Welcome to a geospatial concept module on map projections, a globe to a flat map surface. This concept module was created by the Geotech Center, a National Science-funded project. It is based on the UCGIS Body of Knowledge, Knowledge Area 1, Conceptual Foundations. This concept module will look at why we need a map to be flat and include a datum. We'll also look at problems that occur when going from that globe or sphere to a planar surface or a flat surface. We'll look at some of the distortions for different types of map projections, and we'll look at how some projections use cylinders, cones, and planal surfaces in order to be projected. We'll also look at an important rule of thumb for picking a map projection for your project. Other types of map projections will also be reviewed. I really can't pass up a globe without stopping to spin it and to look at all the continents and everything on that globe, but they're not very convenient. You can't put a globe in your pocket or carry it in your car very conveniently to look at where you're going. So we do have to go from a 3D to a 2D surface to be more user-friendly. Geographic coordinate systems using latitude and longitude and decimal degrees are very useful on a globe, but they don't really include real-world coordinates such as feet or meters or miles. We need to project those features to a flat surface using a map projection and a datum for that projection so that we can have real-world distances, but unfortunately doing this, going from that 3D to a 2D, distortions will occur. In order to project your map from a globe to a flat surface, you'll need to use a map projection, and it will be based on the model of the Earth, geographic coordinate systems, and a datum. Now, datums provide the locational references and sizes of the Earth, and over on the right is just an illustration of some of the things you might consider. Also know that the same map projection can be based on different datums, so just knowing the map projection is not enough. You also have to know what datum was used. If you don't use the correct one, features may be offset from one another, and the amount of offset can be nothing to 300 meters. The map on the lower right shows some of the offsets. Many desktop software options can reproject your data on the fly, but be aware that datum transformations are not done automatically. For highest accuracy, it is advisable to reproject all data into the same appropriate map projections for your project and datum prior to carrying out spatial analysis. If you want to know more about datums, see the datum concept module that's on YouTube. Just note that here is two datums, NAD 1983 and NAD 1927. If you try to combine them, they are not the same. All map projections will be causing distortions when you go from that 3D to 2D surface, and I really like the one on the right where you take the air out of a blow-up globe. You can see you cannot make it flat without cutting into it in some way. And all maps do introduce distortions. One way to remember is SAD. The four properties are shape, area, distance, and direction. The distortion property and degree of distortion can be controlled somewhat. You want to use a map projection that preserves the most important property for the specific need of your application. A little bit closer look, if you think about a globe again and the amount of surface on the Earth that a globe covers from one point to the other, and then you create a flat projection plane in that surface, you can see that you have more details that need to be somehow squeezed into a smaller area. These are another example of that SAD. Shape, it can be distorted. Area can be distorted, distance can be distorted, and the direction can be distorted. Features can be projected on one of generally three developable surfaces, and here we have planes, cylinders, and cones. So these three surfaces that are the developable surfaces and their shape. We're going to look closer at what happens when you try to develop a flat map from a globe using one of these surfaces. So planar map projection, so going from that 3D to the 2D to a flat surface, it can touch the globe in one point, or it can cut through the surface. If the globe cuts the surface, the projection is called a secant. Lines where the cut takes place or where the surface touches the globe have no projection distortion. So here's the two examples where we have a secant, it's cutting through the plane, and you can see the red surface area that has little to no distortion. On the other one, where it just touches in one spot, only at that one spot is there little distortion. Conformable projections. Here's a cylindrical, so we're using a cylinder to project the features on it. You'll note that the parallels and meridians all meet at the right angles. It's conformable in that the angles and the shapes of small objects are preserved, but the size, shape, and area of larger area and objects are distorted. And so this is a Mercator projection. Conic projections use that cone, and here again there's two ways to really look at it. Does the cone touch the surface in one spot, or does it cut the surface in one spot or more than one spot? So on this projection, lines of latitude appear as arcs of circles, and lines of longitude are straight lines radiating to the pole. So cones can touch at one parallel, and if you look at the one on the right where it touches just one, you can see the green area is where there's little distortion, and you can see how it becomes more distorted as you go away from that parallel. Also, you can have it touch more than one, so on the right it's touching and cutting the surface in 2 points, and you can see the green areas where those two parallels are touching are not distorted, and as you get away from those you become more distorted. The Lambert conformal conic projection is commonly used to map North America, and if you look at the illustration on the right, it does give you the state that you often see. Equivalent projections for conic projections, and here again you see that map of the United States, and you can tell this one because it has that curved upper boundary of the United States. It's equivalent, or it's an equal area projection, and it preserves area accurately. Scale and shape are not necessarily preserved, and on the right we have the Albers equal area. Cylindrical projections, you think about wrapping that paper around the Earth as a cylinder. The Mercator projection is the best known cylinder projection, and it is conformable. At any point the scale is the same in both directions. Shape of small features are not distorted, but areas of high latitudes are significantly enlarged. The universal transverse Mercator, often shown as UTM projection, is a type of cylinder projection, and the difference is in the transverse Mercator, the cylinder is wrapped around the poles and not the equator. It's been implemented in international standards, and it was initially devised for use by the military. It uses a system of 60 zones, and each of the zones are 6 degrees wide and has very little distortion within each of its zones. This is what one zone looks like, and it has values, locational values. For Northern Hemisphere, the equator is defined as 0 north. The central meridian of the zone is given a false easting of 500,000 meters east. Easting and northing are both in meters, allowing easy estimation of distances. So each of those UTM zones consists of a zone number, a hemisphere, and a 6-digit easting and a 7-digit northing. And here, this is an example of how that would be written down as a location. Some places you will see the E and the N. Some places it will just have the 14 north and then the two sets of numbers. This is showing how that grid is cylindrically around the Earth. If you'll notice, it starts at 180 degrees and starts out at 0 and progresses around to 180 degrees. This is looking at the US, and you can see the zone numbers 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, progressing from west to east every 6 degrees. One of the important things when you're doing an analysis and you're going to be looking at your data, you need to understand which map projection is the best for your application. So this is a rule of thumb. So these are the three projections: cylindrical, conic, or planar, and this is what is best preserved. So for cylindrical, direction and shape; conic, distance and area; and planar, distance and area. When the correct projection is important on small scale maps, you really want to be able to calculate different things: shapes, areas, distances, and directions. So if you use the wrong projection, you're going to get the wrong answer. On the left, we have the Mercator projection, and it's showing a distance of over 3,124 miles. On the right, we're using that Albers equal area projection, and the distance is shown as 2,455 miles. The actual distance is very close to that Albers equal area projection, where the Mercator projection is really off by a lot. When the projection is not as important is really on large scale maps, so a small area with a lot of detail. The area is negligible for a small region, such as being mapped as a neighborhood. Cities, businesses, policy and management applications often show just a very small area, and so you're okay. One thing is, a lot of the things we see today online, especially on our computers, is Web Mercator. It's used by many online mapping applications such as Google, ArcGIS Online, Bing, and many others. Web Mercator is not truly conformable, and distortions increase as the map locations move from either north or south of the equator. Polar regions are also not included. Some users, and this is the Department of Defense, because they require high accuracy, do not allow these projections to be used within their organization for analysis. ESRI suggests that data be reprojected using updated datums when used with other data, as area and distance calculations may not be accurate. We saw how inaccurate they can be. Esri has a little demo site that's kind of interesting to show the differences. So this is going out to that demo site. We can create a polygon in a region and look at the different values. So Web Mercator is showing an area that is quite different than State Plane or UTM Zone 10. So if you need accurate results, make sure that you have used the correct map projection. There are other coordinate systems in use. State Plane system, which is used extensively across the United States. Within the states, each state has their own State Plane system values, whether there's one zone or multiple zones. Several different types of projections are used in the system. They do provide less distortion within that region of their states, but they can be problematic if you have to cross state boundaries. There's also the public land survey system. You're going to see this as township and range with baselines and meridians. These are the references used in this concept module. If you need more help, there's modules on datums And there's also model courses. I would suggest the Intro Course 101 or the GST 103 as being very useful for understanding map projections. Please see the Geotech Center website for additional concept modules, and we're also developing quizzes on concept module topics, and you can earn a micro credential or a badge. Thank you.